This is the intro video for Algebra 1, and this intro video will be covering terminology and properties. We're going to start off by talking about some properties. The first property is the commutative property, and the way that I remember this one is commutative sounds an awful lot like commute, and commute means to change location, go from your house to work or from your work to your house. So the commutative property of addition looks like this. A plus B is equal to B plus A. Essentially, the order of addition does not matter. You could think of it as 2 plus 7 equals 7 plus 2. Either way, you're going to get 9. This does not hold true for subtraction. So this is the commutative property of addition. There is also the commutative property of multiplication. And this is very similar. A times B is equal to B times A. So with multiplication, the order does not matter. So 5 times 9 is equal to 9 times 5 would be an example of that. This property does not hold true for division. The associative property basically talks about who the numbers associate with, and we group numbers using parentheses. So an example of the associative property of addition would be something like this. Parentheses A plus B, close parentheses, plus C is the same thing as A plus parentheses B plus C, close parentheses. So in other words, if all you're doing is adding, then you can group any 2 or 3, however many you want, numbers within the addition and choose to add those first or add those second, and it doesn't matter. You'll get the same answer either way. The same does not hold true with subtraction. The associative property of multiplication is this. Parentheses A times B times C is equal to A times parentheses B times C. So once again, we're choosing to associate or group specific groups of numbers together, and it's okay to do that with multiplication. It is not okay to do that with division. Maybe you're noticing a trend here. These properties don't really apply to subtraction or division. The next one is the inverse property. The inverse property of addition is A plus the opposite of A, or A plus negative A, is equal to 0. So any number plus its opposite is always going to be 0. So 10 plus negative 10 is 0. The inverse property for multiplication is very similar. You could say B times 1 over B is equal to 1. So if you multiply any number times its reciprocal, and that's a term we've talked about a little bit. So this right here, 1 over B, would be the reciprocal of B. So if you multiply any number times its reciprocal, you always get 1. The exception of that is 0. 0 does not have a reciprocal, so it doesn't work that way. So 7 times 1/7 is equal to 1. The identity property. The identity property for addition is essentially that any number plus 0 is itself. So A plus 0 equals A. Of course, 9 plus 0 equals 9 is an example of that. And then the identity property for multiplication is any number times 1 is itself. So C times 1 equals C, or 12 times 1 equals 12 would be another example of that. Finally, we reach, what do we do with 0? So division properties involving 0, we've talked about these two a little bit in class already. 0 divided by any other number is going to be 0. So as long as A is some number other than 0, 0 divided by A is 0. But if you take some number, A, whatever it is, divided by 0, you get does not exist. It doesn't actually equal a real number, so we would say does not exist. So we're going to use many of these properties as we solve equations in our next unit. But for now, we're going to move on to some real number terminology. So this little diagram involving the real numbers, as I'm looking at this, I realize a couple of things didn't get copied over to this, but we'll fill those in as we go. So the real numbers are going to be the numbers that we deal with here in Algebra 1. There is such a thing as an imaginary number. You really won't dig too deep with that until Algebra 2. So we're going to look at these real numbers in terms of various groups. And please notice the way this is drawn. The big blue box encompasses everything. So everything is within this real number box, but there are specific smaller boxes that lie within this bigger real numbers box. region. So the first types of numbers we're going to look at are rational numbers. And rational numbers can be written as a fraction. And these are repeating. These could be written as a repeating or terminating decimal. So two ways to look at it. If you want to look at it in terms of fractions, a rational number can always be written as a fraction, or it could be written as a repeating or terminating means ending, decimal. So some examples of rational numbers would be 7/3 or -10 ninths, something like that. Those can be obviously written as fractions, so those are clearly rational. Repeating or terminating decimal, 0.3 repeating, so the 3 just goes on and on forever, or -0.64. If it just stops right there, if there are no more decimal numbers, then that would also be a rational number. And then other types of rational numbers would be like 7, -6, 12. Those are all rational numbers because all three of those can be written as fractions as well. So all rational numbers are real, but if we go a little bit deeper here to the integers, all integers are rational. So rational numbers are actually pretty clearly defined. They are ... the set of ... -3, -2, -1, 0, 1, 2, and 3, ... So if you can see that pattern there are no fractions or decimals that are listed, and so integers, basically all the positives, all the negatives, and 0, but no fractions or decimals. And then I'm going to draw in a couple more boxes here. I do apologize for this typo. I think you probably have the same typo in your notes. I don't know why this didn't get transferred over. The next grouping would be the whole numbers. The whole numbers also very clearly defined: 0, 1, 2, 3, ... And then within that group, we also have the natural numbers, sometimes referred to as the counting numbers. This is the set of 1, 2, 3, ... They're the numbers you naturally count with. Okay, so all of those numbers are real. They're all rational. And then we get down to specific integers, wholes, and naturals. All those are contained within kind of that left side. There's one other aspect to this. If there are rational numbers, then maybe there are irrational numbers. So irrational numbers are basically the opposite of rational numbers. They can't be written as fractions. And in terms of decimals, these are non-repeating, non-terminating decimals. And we will deal with irrational numbers this year. So the most well-known case of an irrational number is pi. 3.14159, ... just goes on forever. It never stops, and it never repeats. Another example is a number you'll look at a lot in Algebra 2, maybe a little bit in geometry, and that's the letter E. It's approximately 2.71828, but like pi, it just keeps on going without ever stopping or repeating itself. And then finally, any square root that's not a perfect square. So square root of 7, square root of 31, square root of 10, any of those are irrational. They cannot be written as a fraction. They're non-repeating, non-terminating decimal numbers. Okay, so when you come to class, we're actually going to do a little project with these properties and also the real number terminology here that we've just talked about. And look forward to seeing you in class. We'll work on it then.